Okay, all right, let's get started. So as you have seen the syllabus of module 2, module 2 starts with MOSFET amplifier configuration. That is the first chapter which you need to focus on. Okay, so this is the first chapter which will start today, and other topics are other chapters are MOSFET internal capacitances and high frequency model. Okay, so here we need to analyze at high frequency how the what all the various elements comes into play, especially the internal capacitance and resistances we are going to highlight here. And there is a different model under the high frequency which we call as high frequency model. The model that we have discussed like T model or hybrid pi model, it's basically a small signal model. But there is another model called as high frequency model which we will be discussing in the second chapter of module 2. The third chapter is going to be the frequency response of common source amplifier. This is more or less similar to common emitter amplifier which you have already done in the laboratory. We need to discuss here three frequency bands: high frequency and low frequency response. And finally, this we are going to end with the last chapter of oscillators. Here we are mainly focusing on FET based phase shift oscillators, LC and crystal oscillators, without going more details of deriving expressions for frequency of oscillation here. So these four chapters are quite easier, to study. So let's commence with the MOSFET amplifier configurations. Okay, so this is MOSFET amplifier configurations similar to VGT amplifier configurations. You have different MOSFET amplifier configurations. Okay, so since MOSFET, we know that it is a generally we use it, consider that as a three terminal device, okay, which we have seen. This MOSFET is a three terminal device. Okay, another mark inside here. Okay, so this is going to be the drain, source and gate here. Okay, so since we are going to make each terminal common at one time, and this making common each terminal between input and output leads to three different configurations as you have seen here. Okay, so we are going to make one of these terminals common between the input and output ports here. So that gives us the three configurations. One is a common source configurations, which we call generally as CS configuration, and the second one is common gate configurations. We are going to make a gate terminal common between the input and output port. This is called common gate configuration. And lastly, we have a common drain configuration. So we can construct amplifier from that common drain configuration. So we can call this as a CD amplifier, CD configurations. So these are the three popular configurations which we can develop, using this MOSFET because of three terminals, similar to VGT. Okay. So let's focus on first common source amplifier. This is the first configuration among the available configuration, and this configuration is widely used compared to common gate and common drain configurations, because if you look at its properties, the common source amplifier has got very good properties, the characteristics. Okay, so that's the reason we use common source amplifier. It's one of the most widely used here. Common source amplifier also can be called as a grounded source amplifier. As you will see in the circuit, we are going to ground the source terminal of the amplifier circuit here. Okay, and we will apply the input signal between input Vi, which is nothing but it is gate and the source. This is our input. As you are seeing here, this is the common source amplifier configuration here. If we are not drawing here complete amplifier, but this is going to be the just basic circuit diagram, conceptual circuit diagram. As you can see here, this is here we have a gate terminal. This is the gate of a transistor, and here we have a source. As you can see, source is grounded here, and here we have a drain, and we are going to apply the AC signal here, okay, which needs amplification, which you are labeling here as small Vi. Okay, so this is Vi here. So this is an input signal which is applied between the gate and the source, and we are going to measure output signal between the drain and source here. So this is going to be the output signal here. between which is measured between the drain terminal and the source here. So since source is a common and also source is grounded here, okay, source is also common between the input here. So this is an input port or input terminal, and here we have output here. Okay, so source is basically common between the input and the output here. That's why this kind of amplifier is called as grounded source amplifier here, and is one of the most popular configurations here. And we have here RD to, as I told you in the beginning itself, RD is basically a resistor used to convert a current here into the voltage signal. Basically this is a voltage controlled current source. MOSFET is a VCCS, voltage controlled current source here. Any current, the flowing here, this has to be converted into the voltage here. Basically this is an ID which flows here. So this drain current has to be converted into the voltage, therefore we use this RD, which is nothing but external resistance here. So this is the common source amplifier basic diagram here. Other configurations we will see, and later we can develop amplifier using this common source amplifier. This basic amplifier, we are not connecting any, we are not showing here the bias circuit and other coupling capacitors elements here. Only this contains the MOSFET and the input and output signal, just a transistor configuration. The second type of configuration is a common gate amplifier configuration, or amplifier we can say. So grounded gate also we can say here, because here in this configurations we are going to ground the gate terminal here. So common gate or grounded gate amplifier, which is shown in the figure below here. It's obtained by connecting the gate to the ground and applying input signal Vi between the source and the ground, okay, and taking the output V0 across the resistance RD connected between the drain and the ground. Look at this. This is the basic configuration of common gate amplifier here. Okay, so here you can see that gate is straight away grounded here. Okay, so this gate is grounded here, and wherever you see the ground terminal, that becomes a gate now here. Okay, and the input signal is applied between the source. This is the source terminal here, and there is a drain terminal here. Look at here, this is an input signal Vi, AC signal, which is applied between source and the ground. Okay, here also this is also ground, so here also we have a gate here. Okay, so wherever we see ground terminal like this, that can be called as a ground here. So here also we have a gate here. Okay, so this terminal is also connected here. So though they are at different locations here, so all these gate terminals are same here. So this is input signal which is applied between the gate and source. Okay, so this is an input signal here which is applied between gate and source, and we are going to measure output between drain and the gate here. So drain and gate, which is through the resistance RD. So this point is nothing but the drain point, and we are going to measure output between this drain and the gate here. So through using this resistance RD here. RD is a external resistor connected between drain and the gate here. Since gate serves as a common between input and the output here, so this configuration is called as common gate configuration. And amplifier that we develop using this configuration is called common gate amplifier here. Okay, so next configuration is common drain amplifier. So common drain amplifier, which is obtained by connecting the drain terminal to the ground and applying the input signal between the Vi between the gate and the ground, and we are going to take output voltage signal between the source and the ground across a load resistance RL here. This configuration is known as source follower. An alternative name for the common drain amplifier, which is called as a source follower, because source follows the input whatever we apply here. That's why this configuration is called source follower here. And this is a circuit diagram for the source follower or common drain amplifier. As you can see, let's locate the terminals here. We have a gate terminal here, and source is here. We have a drain terminal here. As you can see that drain terminal is grounded here. So wherever you see the ground, that becomes a drain terminal here. So here also we have a drain terminal. So we are applying input signal between the gate and the drain terminal, so which is an AC signal. Okay, so drain serves as a common between the input. So this is our input here. So though we are applying between gate and the drain, we are also showing here because the same ground terminal is also here. Okay, and we're going to measure output between the source and the drain. Okay, so here also we have a ground here, so this can be called as drain here. Using the resistor or RL load resistor, we are going to measure output across this load resistor here. So this is output signal what we are seeing here. So this is an output voltage here, and we measure output across this. Okay, so this configuration has drain which is common between the input and the output here. So therefore this configuration is called as a common drain amplifier or common drain configuration. Let's summarize this three configurations using this table here. We have the three configurations that we have studied. The first one is the common source configuration, which is the input is applied between the gate and the ground, or between the gate and the source. Source is grounded here, and output is taken between the drain and the ground. Other names are like, it's called as a grounded source amplifier here. Second configuration is common gate configuration. Input terminal is between the source and the ground. Okay, ground is gate itself. Okay, ground is the gate itself. So here we have a gate which is acting like it is connected to the ground, and output terminal is between the drain and the ground, or drain and the gate. That's the output terminal, and this is called as grounded gate configuration, grounded gate amplifier. Configuration and amplifier, we use conversely. So any name is okay because we are going to extend this all three configurations into an amplifier. So therefore sometimes we may pronounce as configuration, or we can also say it is an amplifier. Lastly, we have common drain amplifier. Input terminal is between gate and the ground here. Okay, the drain is grounded in this case, common drain amplifier. Output terminal is between the source and the ground. Okay, and this other name for this is, it is also called as grounded drain amplifier or source follower. So these are the different names for the amplifiers here. Any questions before we move on to the characterizing amplifiers? I hope you understood the three configurations. For examination sake, what is important is you need to write these configurations without making any mistakes. All three configurations you need to remember here. Okay, so mainly the common source, common gate, common drain amplifier here. Okay, so these three configurations you need to remember here. Okay, any questions are there?
Yes, sir.
Okay, so if you don't have questions, let me move to the next configuration, next amplifier, next characterizing the amplifiers. This is very important from a problems point of view, because most of the problems depend on this how do we characterize amplifier. So we'll see here the various formulas that characterize the amplifier. Okay. All right. See, sometimes we may not present a complete circuit. We will show the just amplifier. Now you can see here in this characterizing amplifiers what we are discussing here. we are looking at various parameters that characterize amplifiers here. What are those parameters? We'll discuss one by one. Figure A shows the amplifier fed with a signal source having voltage signal V signal. Look at here, this is the notation we give it for an AC signal here, which is applied here, as you can see here. So this is V signal, small v here, I'll write here for your reference, V here, signal here. This means it is an AC signal here, AC signal that is applied at the input. Okay, there's an AC signal. This can be sine or cosine, that is a signal that needs amplifier here. This is a sine, or it may be even cosine also. And now you can see here the entire circuit, amplifier circuit, different configurations that we have discussed now, which is now common here. As you can see, we are representing that amplifier configurations with a triangle symbol like this. This is an amplifier here. This can be common source, this can be common gate or common drain amplifier here. Okay, so here you can see that the signal that we are applying AC signal to the input, its resistance, internal resistance, we can show it as R signal here. Okay, so many times we have a doubt here, what is this R signal here? So remember that we are showing this internal resistance of this AC source using a physical resistor here called as R signal here. Okay, so in laboratory, we may not have this, but by default our AC source will have this resistance. But while modeling, we need to show this as external resistor here. Otherwise, we may feel that this supply doesn't have a resistance here. So that's why we are showing that as a physical resistor here. So this is an R signal, which is an internal resistance of this AC source here. And apart from that, we have here another set of parameters, inputs like VI. We have shown that there is a lot of difference between the input signal that we measure here with reference to ground to that of V signal. We know that VI and V signal, they are related with voltage division rule. We'll arrive at a mathematical equation using voltage division rule, the relationship between VI and V signal here. Under what conditions this V signal becomes equal to VI? This is very important for that. When we make this as 0, now see here, the entire AC signal that we apply, okay, will be appearing across the amplifier input here. So VI is nothing but amplifier input signal, and II is the current due to the input signal, which is VI here, which is II here. Okay, so II indicates here it is an input current. So you can see the subscript here that we have denoted here, I with small I. It is nothing but amplifier input current. When we indicate like this VI, this is nothing but amplifier input voltage, and this is an AC signal that needs an amplifier, that needs an amplification. And here we have an internal resistance of this AC source here. And complete amplifier circuit now we are showing with a triangle symbol like this. Here we can have different sort of amplifier configurations like common source, common gate, common drain kind of configurations. And the output current of amplifier is denoted as I0 here. So I is basically current, I0 indicates it is an output current here. And here we connect external resistance or L. Sometimes we use this as RD also. Okay, RL and RD we use equivalently. So students can use any one here. Okay, so RL is nothing but which is a load resistance here, which is connected to convert this current into the voltage here. So V0 is nothing but the output signal. I hope you have understood this basic amplifier circuit here, which is this is complete amplifier circuit here. And now we will see different parameters that characterize the amplifiers here. Okay, let me read out here the points here. Figure A shows an amplifier fed with an AC signal V signal and an internal resistance by R signal. The amplifier is shown with a load resistance RL connected to the output terminal. Here RL can be an actual load resistance or input resistance of the succeeding amplifier stage. So this also will represent an amplifier resistance for the succeeding stage here when we connect amplifiers in the cascade fashion. Okay, here we have an equivalent circuit since we already familiar with hybrid pi model, that model can be used here to derive the parameters here as you are seeing here. This amplifier is now replaced with an input resistance here, which is an Rin. So Rin represents an input resistance now. These things remain same. You can simultaneously look this circuit, an amplifier circuit, which we have shown, because the reason why we have shown here triangle symbol is to reduce the complexity here. Okay, so our intention is just to see the formulas, that characterize the amplifier here. For that reason, here this instead of writing complete amplifier circuit, we have shown with a triangular symbol here now. Now we are writing here just below the equivalent circuit, the equivalent circuit of the amplifier here. The equivalent circuit of amplifier comprises this input resistance and a dependent voltage source, which is AV naught into VI. So this is nothing but it's not voltage source, it's a current source basically, AV naught into VI, or GM into VGS, you might be aware of it. So that is the current source here, as you are seeing here. So R naught is going to be the load resistance, which is a physical resistance that we connect here, and V naught is nothing but the output voltage that we measure across the RL here. Okay, so this is an equivalent circuit of the amplifier circuit, what we have shown here. These are the three things which any amplifier will have. So what are three things here? One is going to be the input resistance, another one is going to be the voltage gain or output voltage, which you can write it as AV naught times VI, that is the output voltage, and R naught is going to be the output resistance. Okay. So another this circuit will come back at the end, because here this circuit is just the equivalent of this, which we are modifying this amplifier circuit only to measure the output resistance here. So when we measure output resistance, okay, the effect of input signal should not be there. So therefore here in this amplifier circuit, what we do is we will just make a signal source as 0. So once you make V signal as 0, then by default VI also becomes 0. So VI is 0 here. As you can see, the input is short circuited here, and so there is no amplifier input here when we measure the output resistance of an amplifier. So now we are connecting a temporary current source here, as you are seeing here, so which has got a current of Ix here, and if we know the voltage between this point and the ground, and okay, the current here, so then we can easily calculate what is this R naught here. So R naught is nothing but it is Vx by Ix here. Okay, so using this simple diagram, okay, so this we can calculate okay, the output resistance of the amplifier circuit, just only this part here. So while measuring output resistance, the effect of input should be made as 0 here. So we'll come back to this later on, and we'll explain how we can make use of this configuration or circuit to obtain the output resistance here. Okay. Any questions about this? We have just discussed an basic amplifier circuit. Okay, without making much complex, we have just take a simplified amplifier circuit here, and other things like signal source, signal resistance, and load resistance we have shown outside the amplifier circuit. And later we have written equivalent circuit of the amplifier circuit, which contains input output resistance and an voltage output voltage, which is voltage source, which is AV naught into VI. So these are the basic things of an amplifier. Now let us focus on the different formulas that characterize the amplifier. The three parameters in characterizing the amplifier performance are as follows. The first one is going to be the input resistance. So any amplifier circuit should have a very high input resistance. What is the reason behind this having high input resistance here? We're expecting here this Rin should be very large. So when Rin is very large here, basically this the signal, these two things here, this V signal and Vi, they tend to become equal here. Okay, so we'll see that in a short here how they become equal here. But formula here is for to calculate input resistance is remember this is an amplifier input resistance. Okay, so amplifier input resistance, when we see the amplifier at the input here, okay, how do we measure resistance? To measure resistance, we need to have a input voltage and input current. So simple formula is VI divided by II. Okay, so that is the amplifier input resistance. So the amplifier input resistance, which is denoted as Ri, which is equal to amplifier input signal and amplifier input current here. So if we take a ratio of these two things, we get an amplifier input resistance. Now we'll see alternate versions of this formula, input resistance here. So Vi, as I told you, Vi and V signal, they are related by the voltage division rule here. Vi and the V signal, as you can see that we can write this formula based on the voltage division rule. You can look at the circuit here. I am writing just Vi in terms of V signal here. So Vi equals V signal times Rin divided by Rin plus R signal. Okay, the same relation is used here, as you can see here. So Vi is equal to V signal times Rin divided by Rin plus R signal here. So this is the equation relating Vi and V signal here. Okay. I also told you that when we make R signal as 0, what is going to happen? As you can see that in this formula, when we make R signal as 0, you can see that this Rin cancels here, and this V signal is going to become equal to Vi here. Look at circuit, what do you mean by that? So when amplifier input resistance is 0, the complete AC signal appears at the amplifier input. That means this Vi is going to become equal to V signal, okay, when this becomes 0. Resistance 0 means it is going to be a short circuit here. Okay, when this is a short circuit here, this input signal, amplifier input signal, becomes equal to the AC signal here. Okay, so that's what even the formula also shows you that. Next thing is going to be the open circuit voltage gain. So these are the various parameters that will characterize the amplifier. Open circuit voltage gain, which we denote it with AV naught. Okay, AV basically is a voltage gain. AV naught indicates which is the open circuit voltage gain. So that means we have to make here the load resistance as infinite and calculate the voltage gain. That's very simple here. It's the voltage gain obtained with nothing connected across the output here. So we have to make a load resistance as infinite here. That means very large load resistance here. Remember that this will characterize again the performance of an amplifier here. AV naught is another important parameter. This is measured by making load resistance as infinite. Our load resistance is very large value. And formula for that is again, when the RL is infinite, under that condition we have to calculate output voltage and the input voltage. The ratio of V naught by Vi under this condition gives you AV naught, open circuit voltage gain. Okay. Any questions about this? This is another formula, another equation that characterizes the amplifier. Let us give some equation numbers so that you can remember them easily. So for this you can give equation number as 1, and this Vi and V signal relation we can give equation as 2, and AV naught we can call this as equation number 3. Okay, next let us go for the measurement of output resistance here. Output resistance is denoted as R naught, capital R into R subscript with O. R naught is the resistance looking back into the amplifier output terminal with Vi is set to 0. Okay, as we have shown already the diagram here, when we want to measure the output resistance looking from the output side here back to the amplifier input here, this is the direction which you need to look, and looking at this, the resistance what you measure is denoted as R naught. This is the output resistance, and here we need to make input signal as 0. The effect of input AC source should not be there, so therefore we are going to make Vi as a 0. Okay, now let us arrive at the equation connecting this R naught here. Okay, so we have Vx divided by Ix. Vx is a temporary voltage source that is connected at the output, and the current that resulting from that is denoted as Ix here. So here we can connect voltage source, and current that resulting from that can be denoted as Ix here. Ratio of Vx by Ix gives you the R naught with Vi as equal to 0. So these three formulas I hope you are familiar by this time now. R naught, okay, is nothing but this equation which you need to be familiar with. Okay, so this is used in solving problems also. Okay, so now let us see the Thevenin's equivalent voltage of the amplifier output circuit and the output voltage V naught. We can have a relation here. Okay, so this equation is again very simple. Looking at the second circuit here, look at this circuit here. Okay, looking at this, we can write equation for output voltage. How do we write equation for output voltage? V naught, again apply voltage division rule. V naught can be written as this voltage, entire thing is a magnitude of voltage here, AV naught into VI. That should be multiplied with RL divided by sum of R naught plus RL here. That is the voltage division rule. Okay, when we want to find a voltage across any resistor, we need to multiply source voltage with the resistor and then divide with sum of these two resistors here. Okay, so V naught is nothing but this AV naught into VI times RL divided by R naught plus RL. So this gives us a relationship between V naught and the VI. Let us move to the that equation. As you can see here, V naught is equal to AV naught times VI. This is the source voltage, as you are seeing. That's multiplied with RL divided by RL plus R naught, sum of the two resistors here. Okay, so this is also called as Thevenin's equivalent voltage. Okay. Now from this we can write different equations also. The voltage gain of the amplifier AV is nothing but V naught by VI. Okay, let us call this as equation 6, and here this equation V naught in terms of AV naught, let us denote it as equation 5. So in front of us we have equation 5, 1 to 6 equations. AV is nothing but it's a definition, it's V naught by VI. So now we can find out equation 5 in equation 6 if you substitute here. So for V naught you can substitute here. Okay, so this V naught equation 5 you can substitute here, and let us see what equations you get here. AV is equal to, okay, V naught by VI now goes to, you can also write from this straight away, V naught by VI is nothing but AV naught into RL divided by RL plus R naught also. That's what we have written here, and we have called this as equation 7 here. Since here we have V naught here and here we have a VI, this can be moved to the left hand side, so you get V naught by VI. Left out is AV naught into RL divided by RL plus R naught, so which is the equation given here. Next is overall voltage gain, which is denoted as G. So these are the notations which you need to follow as per the textbook notations here. So G is shown here for overall voltage gain. So GV indicates its voltage gain, G indicates overall gain. Okay, so which is V naught by V signal. If you take a ratio of output voltage to the AC input here in this circuit, as you are seeing here, if we take a ratio of this with this, that gives you overall voltage gain. So generally the formula for G is nothing but GV is nothing but it is V naught divided by V signal. Okay, AV is nothing but it is V naught by VI. So look at the difference here. AV is nothing but which is V naught divided by VI. Okay, that means when we measure output voltage, if you take a ratio of V naught versus VI, that gives me the AV, and when you take V naught divided by V signal, that gives me the GV. That is the difference here. Okay, GV is basically a subset of AV. Okay, so let us see that what values you get it when we solve a problem. You get to know the relationship between AV and GV and also AV naught. We also discussed about AV naught. AV naught is nothing but when we make this RL as infinite, the gain that we get is AV naught. Okay, and we have a formula we have shown for AV naught here. Okay, so what is AV naught formula? AV naught is here. Okay, AV naught is nothing but VL by VI. This is with RL is equal to infinity. So we understood now GV. GV is nothing but V naught by V signal. Now we can arrive at even the equation for GV also. Okay, so from equation 2 we have V naught. You can see here equation 2. We have VI equation here. Okay, so from equation 2 we have VI is equal to VI and V signal, they are related by this formula, and we can write this V signal as just by cross multiplying this with VI. Okay, we can write this as V signal as Rin plus R signal divided by Rin into Vi. So these things you can substitute in this GV, okay, because we know that GV formula is V naught by V signal. So just derive for V signal and you can substitute in this. So V signal formula is here. Now we can substitute equation 9 in equation 8. So we can arrive at equation for the GV here. Also we know that V naught equation. So V naught equation we have here somewhere we have derived here. Where is the V naught? V naught equation. Here equation 5 is here, which is V naught equation. So V naught equation is nothing but equation 5, and V signal is nothing but the equation which you can obtain by altering this, cross multiplying this, and we get V signal, and those two equations you can substitute here. Okay, V naught and V signal equation. That is what it is done here. You can see here. So this entire thing is V naught. Okay, so numerator part. Okay, and this is the denominator part. Okay, you can see that this Vi cancels here. Okay, we can separate out terms here, A in AV naught, and this Rin we can take it to numerator. You can write it here. This is first term, second term, and totally third term here. Though it is a lengthy equation, it's very easy to remember that, because here there are two resistances here, Rin and R signal. Here we have RL and R naught. Okay, so you can also observe here, this is a parameter that has got both input resistance and the output resistance here. Okay, so this is GV. Okay, so GV is overall voltage gain. Okay, in terms of AV naught, you can see here. Okay, so this equation, students, you need to remember that, because this we are using in solving problems also, GV. Okay, so when you know the formula, it's very easy to substitute and obtain solutions for the numericals. So I suggest all of you to memorize these formulas, write down all these formulas that you have derived so far at last page of your notes, and so that you don't forget it, while solving the problems here. Now let us pick up all three amplifiers and derive the parameters for all these three amplifiers. Remember, in examination they may ask you any of these parameters, or they may ask you to derive relations that characterize the amplifiers also. In such case, you need to show all these equations when they ask about characterizing amplifiers. When they ask about basic amplifier configurations, you just need to write three different configurations and explain, the input where we give and output where we measure, and which is common between the input and output. So those things you need to explain for the three configurations. Okay, that we have discussed here. Okay, any questions before we move on to the common source amplifier? Okay, let's move to the common source amplifier. Common source amplifier is one of the most widely used amplifier. Okay, this is similar to the common emitter amplifier with reference to BJT. Okay, as you can see here, this is common source amplifier. Okay, so this is, again, we are not writing here complete amplifier circuit. This lacks with coupling capacitor, bypass capacitors, all those things. This just contains, usage of MOSFET as a common source amplifier. Okay, so you can see here we are applying AC signal here that needs that need to be amplified, and we have already discussed about R signal. This is an internal resistance of AC source, and Vi and Ii, though some few things here may be missing here. So Ii is nothing but which is an input current here, amplifier input current, and I naught is nothing but amplifier output current here. Few things you need to remember here. Vi is the amplifier input and V naught is the amplifier output. Rin is the input resistance of the common source amplifier. R naught is the output resistance. We are showing here arrow mark to indicate that how we measure the input resistance, and here this arrow mark shows how do we measure the output resistance here. Okay, and examination point of view, you may have to prepare for the derivations of input output resistance, open circuit voltage gain. Those things you need to remember here with reference to this circuit, common source amplifier circuit. Next we can arrive at equivalent circuit as you are seeing here. Okay, so just we have replaced this MOSFET with its hybrid pi model. We have discussed this in the earlier class also. We are replacing gate and source with a open circuit as you are seeing here, and we are replacing drain and source with a current source here, and R naught is nothing but the resistance due to the channel length modulation effect. Now this MOSFET, what you are seeing here, the symbolic representation in the common source amplifier, its equivalent is nothing but these three elements here. One is open circuit here, okay, and the current source and R naught. So these three elements represents a MOSFET equivalent circuit. Rest all things are retained as you are seeing here. Only thing is we have just replaced this symbol with its equivalent circuit here. We can draw even a rough diagram like this. A MOSFET with its equivalent is shown like this. So this is the MOSFET equivalent. The diagram what you see here, now it has got this. Rest all terms we have attached as it is, you can see here. Okay. So this is the equivalent circuit here. Why we need to draw the equivalent circuit of a MOSFET here? Because here, as you can see, we don't know internal elements of a MOSFET here. By drawing its equivalent circuit, we are going to become familiar what are the elements that we see inside the MOSFET here. So that gives more clarity on developing, or characterizing the amplifiers here. Assume that we don't have the equivalent circuit now. So while calculating the output resistance here, you don't have an information of what are the resistance we see at the output here. Okay, so therefore this writing an equivalent circuit is very important here. Okay, so this helps us to understand more about the amplifier in general here. Okay, hope you understood the importance of this, each and every element here and the equivalent circuit here. Okay, so using this equivalent circuit now we may ignore this and we may start working on this. We'll consider this equivalent circuit and write equations for various amplifier parameters here. We'll take one by one. What are the characterizing parameters of an amplifier here? The first thing is going to be the input resistance here. So as you can see here, the input resistance here, since it is an open circuit, okay, so this we got to know when we have drawn here the equivalent circuit of an amplifier only. Otherwise, what we can think here is, blindly you may think that there may be some input resistance here. The moment we have drawn the equivalent circuit, now we can say directly that between the, see the input resistance where it is measured, between the gate here, this is the gate common source amplifier, and the source. When we measure the impedance between the gate and source, obviously it is an open circuit, so input resistance is going to be in infinity. So without doing any derivation, straight away we can write here the input resistance is infinity. So the input resistance is infinity because between the gate and source, as per the amplifier equivalent circuit, it is an open circuit. So therefore input resistance is infinity. The output voltage V0 can be found by multiplying the output current Gm into VGS by the total resistance between the output node and the ground. What do you mean by that? The output voltage here, as you can see here, this is the output voltage here. We have denoted here V0. This can be obtained by just multiplying the current with the resistance. These two resistors, what you see, one is internal resistor and the other one is going to be the external resistor. We can make it as a single resistor because those two resistors are a parallel combination, right? So we can also write this to our these two resistors are equivalent to one resistor like this, and this is nothing but an R naught parallel with capital RD. This is the internal resistance due to the channel length modulation effect or early effect, what we have called, and RD is the external resistor RD here. Okay, so now across this we have a current source, the current source here. Look at the current here, which is going to the ground here. This value is Gm times VGS. These two are connected like this. Now here we have a output voltage. Now output voltage can be easily estimated. The current that is flowing here is nothing but Gm times VGS times this resistor here. So we can write a simple equation, V naught as minus Y minus, because the current is leaving this node here, this particular node here, minus Gm times VGS, that is the current, multiplied with the resistance, which is R naught parallel with RD. So you see that how simple we have obtained the equation. Okay, and look at here, this VGS also is equal to Vi. So this VGS what you are seeing is also equal to Vi. Now see, we obtained a gain, right? V naught is here and Vi is here. We can easily obtain voltage gain for this amplifier. So what is V naught by Vi? So which is nothing but minus Gm times RD, R naught parallel with RD. Same thing which is done here, you can see here. So look at here, this is the expression for the output voltage V naught minus Gm times VGS. This is the current term, first one. There is the equivalent resistance here, current, resistance, and negative reason I also told you, because current is leaving the node, it's negative. And next we have VGS is equal to Vi. We can substitute in this equation and we can obtain the AV naught, which is nothing but V naught by Vi or V naught by VGS. Okay, in this case V naught and Vi and VGS both are same. Okay, so we can write here okay, AV naught as minus Gm times RD parallel with R naught here. Okay, the total resistance R naught also can be calculated by just looking at from the output terminal here. When you see from the output terminal, these two resistances becomes parallel here. So therefore output resistance is RD parallel with R naught here. Okay, so this is simple equation here. Since the transistor output resistance R naught reduces the magnitude of the voltage gain, we can also neglect R naught here. Okay, so usually this R naught is value is going to be very large compared to RD. So since it's a parallel combination here, R naught can be neglected here. So once we neglect R naught, this AV naught equation, so R naught is neglected here because it reduces the voltage gain. So if we do that, so what will be the equation for AV naught? AV naught is nothing but minus Gm times RD here. Okay, and also look at output resistance now. We said that earlier output resistance is this, including the both the effects here, RD and R naught. Now due to the R naught, which reduces our output voltage gain, so therefore you can ignore this. In such case R naught becomes equal to RD here. Okay, and lastly we have overall voltage gain. This is very simple. Overall voltage gain is denoted as GV, and we already know this AV, okay, equation, minus Gm times RD parallel with R naught parallel with RL. Okay, so you can see here this entire signal, if you assume it is appears Vi is equal to since input resistance is infinite. Okay, so we can make this Vi is same as V signal. If that is the case, you can see that GV is equal to V naught by V signal and V naught by Vi. So V naught by Vi is nothing but AV equation that is shown here, which is Gm times RD parallel with R naught parallel with RL. So again the equation for Gm or AV both are same with reference to this case. So which is equal to minus Gm times RD parallel with R naught parallel with RL. So these final equations which is written in box we should remember here. Okay, so those are the one which we use it in solving the problems here. Okay, so once you are done with that, these are the few observations. The input resistance R is infinity for the common source amplifier. Output resistance is just moderate to high. We don't have very high resistance in common source amplifier. We expect this to be low, but here in this case it is moderate to high. Open source voltage gain, open circuit voltage gain is AV0 is high, and bandwidth is limited for this common source amplifier, because you can see the umbrella shaped curve for this frequency response of common source amplifier. Okay, so with that I think we have done with common source amplifier. Next class we'll take up a problem and help you to understand more about common source amplifier. Okay, any questions so far about common source amplifier? Look, at today we have discussed basic configurations, characterizing amplifier, CS amplifier without source resistance. Next class we will discuss CS amplifier with RS, and we also discuss source follower, which is nothing but common drain amplifier. Okay, that's all for today. Okay, any questions are there, we'll take up in offline.